Hello, everybody. Let's look at this question. What is an electrolyte? We've heard this word before, particularly if you drink Gatorade or something like that. They've made a gajillion dollars selling you on the idea of the importance of electrolytes. But I think a lot of us aren't exactly sure what is it that makes an electrolyte or what is it that's exactly going on there. So let's talk about what an electrolyte is. And broadly, there are three criteria, three things that we would look at for classifying something as being an electrolyte. Number one, we would be looking at something that is an ionic compound. An ionic compound. So, probably worth it to take a second and quick review that. What are we exactly looking at there? Something that is some combination of a cation, an anion. That cation is typically going to be some sort of metal, could be a polyatomic ion. That anion is going to be a non-metal or a polyatomic ion itself. And there's even some combinations where you could have polyatomic ions for both. You'll have a polyatomic ion cation, a polyatomic ion anion. Remember, the bottom line is this cation is positive, anion is negative. That's important. It has to be ionic compound. Second, it must be aqueous. Love using vocabulary words here. Aqueous. Good time to define this word as well. Aqueous means that the substance is soluble in water. That means it can dissolve in water. We know salt is a good example of something that is soluble in water. Sugar is something that is soluble in water. As we're going to see with this third qualifier, though, one of those is an electrolyte, one of those is not. And in fact, the one that's not fails on the first criteria, even though it's okay on the second. And that third one is that it dissociates in H2O. So not only is it dissolving in water, it's dissociating in water. And that's where sugar fails. And sugar fails that largely because it's just not ionic. There are some ionic compounds, however, that are not particularly soluble in water and do not dissociate in H2O either. But you must meet all three of those criteria to be an electrolyte. All three of those criteria. Within those three criteria, we can actually go in there and break that dissociation part down a little bit more than just saying it just strictly dissociates. There are levels of dissociation. And we break those down by saying that an electrolyte can either be strong or it can be weak. And folks, if you're going to get farther in your study of chemistry and you get into acids and bases, there's a good possibility that this distinction will become particularly important when you get there. In basic solubility, a lot of times we don't get farther than just saying electrolyte, non-electrolyte. But we are going to get into what it means to be strong and weak now, because there are some important distinctions in terms of the properties of electrolytes and the differentiation between strong and weak as a result. A strong electrolyte dissociates 100%. A weak electrolyte dissociates way less than 100%. Sometimes we just say less than 100%, but the reality is it's way less than 100%. In fact, sometimes it's actually mathematically inappropriate to even say percent, because even at 1%, you could be talking about a ratio that's much too high. You might only have one out of every 10,000, 100,000, million, billion, even less than that molecules actually dissociating in H2O. Now, maybe you've been sitting here for the last minute, 90 seconds saying, you said dissociate 40,000 times. What does that word mean? All right, because that's a big piece of the puzzle. What does it mean to dissociate? Let's clear everything here and let's talk a little bit about what it means to dissociate. To dissociate means that water molecules are breaking apart this ionic compound into its constituent ions. Water molecules are pulling the ions apart into its constituent ions. What the heck am I talking about here? Let's look at a classic example of an electrolyte. Good old Na. Let's make this actually much larger. NaCl. not drawing for size here. All right, sodium chloride. In that sodium chloride compound, we know, or we can figure out by looking at the periodic table, that sodium, based on its location, is a metal. Metals make cations. So we know that sodium is the positively charged ion here. Chloride is the negatively charged ion. In other words, chloride has taken an electron away from sodium. Sodium is given that electron away to chlorine. Chlorine becomes the -1 chloride ion. Sodium becomes the sodium ion. What holds them together is the positive-negative attraction that opposite charges will have for each other. And ionic bonds are very, very strong, much stronger than things that are covalently bonded. So this is a good attraction. But along come water molecules. Let's draw them in this color. Now, let's draw a separate water molecule over here just so we can have a separate discussion about this first. Again, not to scale. Here's my O, here's an H, here's an H. Water molecules, they look like little teddy bears. They look like a Mickey Mouse. Don't come after me, Disney, please. All right. They look something like that. The two little H's look like the little ears. And then this O, I've drawn an O in the middle here so we can kind of see it. But this large piece here is the oxygen itself. Okay. So let's erase that little. All right. There's my water molecule. My point here is this. This oxygen side of the molecule is very negative. Why is that? Oxygen is a nonmetal. Therefore, it is very electronegative. Therefore, it is attracting the shared electrons, because there's still shared electrons between it and hydrogen, closer to itself. Compound that with the fact that there are two unshared pairs of electrons, which I've just drawn here, and the O side of a water molecule is very negative. The H side is very positive. That's why water is a polar molecule. So polarity is a big piece in this. And hopefully that starts to unravel why being an ionic compound is such a big piece of being an electrolyte. So water molecules can begin to surround this NaCl. Now, I'm not going to draw the letters inside the water molecule, but let's just draw some water molecules like this. And notice I've drawn them in each case so that the oxygen and the negative side of the compound is closer to the Na. In each case, at the 12 o'clock position, over here at 9 o'clock, down here at 6 o'clock. That's very important because that oxygen side is going to be very strongly attracted to the positive side of the Na. Conversely, water molecules that surround the chloride side are going to orient themselves like this. And notice now I am drawing that's not a very good water molecule. We can do better than that. Doesn't look like a Mickey Mouse at all. We want to have a representation that shows that the hydrogen side of the molecule is close to the chlorine side because the hydrogen side is the positive part of the molecule. So if I see the positives here being represented right here, that's attracted to the negative part of the chlorine. H is here, attracted to this negative charge. H is here, attracted to this negative charge, and vice versa. The attraction is strong enough that what happens is this molecule is dissociated. The word dissociate, D-I-S-S-O-C-I-A-T-E, great spelling bee word, dissociate. The word dissociate is the opposite of the word associate. Associate means to bring things together. An association is a grouping of things that have something in common. If you are a sports fan, you may follow the NBA, the National Basketball Association, a group of teams that play basketball with each other. Associate is the opposite of this word. So if I say dissociate, instead of bringing things together, I am pulling them apart. So these water molecules actually separate this sodium chloride unit into a separate sodium and chloride ion. So now let's go back and draw a sodium. Let's call this the before. So this is before. And now let's call this down here the after. So water molecules surround. And now here's my sodium. Here's my chloride. I'm going to space them out because check out how I'm going to draw the rest of this now. Let's go back to the H2Os. I now have these water molecules surrounding my sodium ion like so. Notice that, and I've drawn them butt up next to each other, but I want to make it very clear they are not bonded to each other. Not bonded to each other. Attracted, yes. Bonded, no. Na still has that positive charge because it's lost that electron to the chloride. And over here, this chloride ion is surrounded by water molecules as well. And imagine the three-dimensionality of this, folks. So there's going to be some in front and behind the sodium and the chloride ions that I'm drawing as well, not just all in the plane of the screen that we're looking at. So surrounded by water molecules on all sides like this. That's dissociation. Why do we call that an electrolyte? Because these separate ions now have the ability to carry charge in aqueous solution. This is the reason why, folks. Now, there's a common misconception that water conducts electricity. Pure water does not. Pure H2O is a covalent compound, so polar covalent, but covalent. It does not dissociate into ions. When something dissociates into ions, as we see here, those sodiums and those chlorides have the ability to migrate between between two poles, let's say. There's fancier terms. I don't want to get into the electricity aspect of it too much. To create a flow of charge back and forth. That's what allows H2O to conduct electricity. Its impurities, particularly something like salt water, like ocean water, has got a lot of salt in it. All that salt that's in ocean water. Think about how salty ocean water is. If you've ever been to the ocean, you ever got splashed in the face, or if you've ever gargled with salt water, if you have a sore throat. I don't even know why that's really a thing, but I know that is a thing. And you know how that kind of tastes. So you know there's a lot of salt that's in there. All those ions have the ability to carry charge through there. That's what makes something an electrolyte. That's what makes something an electrolyte. So in the aqueous state of matter, ionic compounds have the ability to conduct electricity. In the solid state of matter, they do not. Salt in your salt shaker isn't conducting electricity. Salt dissolved in ocean water is conducting electricity. Now, if we go back to that discussion about strong versus weak to kind of finish up this discussion, we might remember that we talked about strong were things that dissociate 100%. Weak were those that dissociate less than 100%. Compounds like sodium chloride are strong electrolytes. Strong electrolytes. Every single sodium chloride unit that you add to any volume of water, whether that's a glass or the ocean, is going to dissolve until it reaches its saturation point. And saturation points vary from compound to compound. A lot of things that are classified as salts, because sodium chloride, which we've drawn here, is not the only salt that's actually in ocean water. They are strong electrolytes. A lot of my compounds that are made out of the group 1 metals, a lot of my compounds that have halogens in them, my nitrates, if we're talking about polyatomic ions, my ammonium compounds, if we're talking about polyatomic ions, chlorates, all those fit under the umbrella of strong electrolytes. They dissociate 100%. Now, unfortunately, even there are some exceptions. You can certainly find some things like baking soda is a good one. Sodium bicarbonate. Sodium bicarbonate does not dissociate that great in water. It does, but for a sodium compound, it's kind of weak. So my strong electrolytes tend to be my group 1 metals, compounds that have my group 1 metals, compounds that have a lot of my halogens, particularly my chlorides, my bromides, my iodides. I'm going to draw minuses here so we remember that we're talking about ions. Polyatomic ions such as my nitrates, my ammonium compounds, NH4+, and my chlorates. Very loosely speaking, those are my strong electrolytes. A lot of my weak electrolytes, my weak electrolytes really make up just about everything else that fits the criteria on the first screen. Ionic compound, soluble in water, dissociates into ions. So you get a lot of situations where maybe you have some of your transition metals, you have some organic polyatomic ions, if that word is familiar to you, polyatomic ions that contain particularly carbon, but carbon-hydrogen bonding in them. It's very tough to make generalizations there. When you get to acids and bases, the differentiation between strong acids and strong bases and weak acids and weak bases becomes much more important. At this level, usually when we're talking about solubility and electrolytes, we're really just talking about the 3 criteria that we initially. And I'm going to say it one more time to wrap up. We're talking about substances that are ionic, substances that are aqueous, in other words, they dissolve in H2O, and number 3, they dissociate into ions. Hopefully that helps you out in answering the question, what is an electrolyte? Take care, folks.
Thanks everybody for watching my video, and I hope you're looking for some more. If so, check out the links below in the description to find out more information from my webpage and from all of us at Science Empowerment New Jersey, where we mold minds for science.